So which is the larger expression? The 99th root of 99 or the 100th root of 100? If we observe the two expressions, we can see that the 99th root of 99 has the smaller base but the larger exponent, since the 99th root means an exponent of 1 over 99 and the 100th root means an exponent of 1 over 100. So the 99th root of 99 has the larger exponent. Actually, let's just rewrite the expressions as 99 to the power of 1 over 99 and 100 to the power of 1 over 100. So we're trying to determine if the expression with the larger base or the larger exponent will result in the larger overall expression in this case. Let's express 99 to the power of 1 over 99 as f of 99 and 100 to the power of 1 over 100 as f of 100, where we define f of x as x over 1 over x. We just need to show that this function is either monotonically increasing or decreasing to determine if f of 99 or f of 100 is greater. To determine if f of x has the monotonicity property, we should try differentiating f of x and see if it's always positive or negative in the domain we are interested in. So let's find the derivative of x to the 1 over x. Before I take the derivative of both sides, I'm just going to take the ln of both sides to get ln of y equals ln of x to the 1 over x. Then I'm going to use the logarithm rule for exponents to rewrite the right-hand side as 1 over x ln of x. And what I've done is I've taken the 1 over x exponent to the front of the logarithm as a constant multiple by using the power rule of logarithms. We can rewrite the right-hand side as a fraction, so ln of y equals ln of x over x. Alright, so now we can differentiate both sides in respect to x. If we differentiate ln of y in respect to x, we end up with 1 over y, which is the derivative of ln of y in respect to y, and then we have to multiply that by dy dx because of the chain rule, which is what we need to use when we do implicit differentiation. And this is equal to the derivative of ln x over x in respect to x. And to do this differentiation, we need to use the quotient rule. The derivative of ln x over x is the derivative of the numerator, which is 1 over x, which is the derivative of ln of x times the denominator, which is x, minus the numerator, ln x, times the derivative of the denominator, which is 1, because the derivative of x is 1, and all of this is divided by the denominator squared, which is x squared. So this is just applying the quotient rule. If we simplify this expression, we end up with 1 over y dy dx equals 1 minus ln of x over x squared, and I just multiplied 1 over x by x to get the 1, and the minus ln x times 1 just becomes minus ln of x. To isolate the dy dx expression, we need to multiply both sides of this equation by y, and if we do that, we end up with dy dx equals y times 1 minus ln of x over x squared. And we originally set y equals x to the 1 over x. So this means dy dx is equal to x to the power of 1 over x times 1 minus ln of x over x squared. So right now we need to determine if this expression representing the derivative of f of x is always positive or always negative in the domain we are interested in. If the derivative is always positive or always negative, we can infer monotonicity of the original function. Let's focus on the 1 minus ln x part of the expression first, which is the numerator of the fraction. Ln x is the natural logarithm of base e, where e is Euler's constant, so we know that ln of e is equal to 1. Since the logarithm is a strictly increasing function, we can infer that ln of 3 is strictly greater than 1. We might not know what the exact value of ln of 3 is, but we can be sure that it's definitely greater than 1. And since the function is strictly increasing, we can say with certainty that ln of x is greater than 1 for all x greater than or equal to 3. So if we look at the expression 1 minus ln of x, assuming x is greater than or equal to 3, we know that ln of x is greater than 1, so that means 1 minus ln of x would definitely be a negative number, so it's strictly less than 0, assuming that x is greater than or equal to 3. So 1 minus ln of x is less than 0 for all x greater than or equal to 3. X over 1 over x is also greater than 0 for all x greater than or equal to 3. Since x would be a positive number, 1 over x would also be a positive number, so we have a positive number to the power of a positive number whenever x is greater than or equal to 3. So x to the 1 over x is definitely positive, and x squared is also positive when x is greater than or equal to 3. So if we look at the expression for dy dx, x to the power of 1 over x is positive, 1 minus ln of x is negative, and x squared is positive. So we have a negative value, 1 minus ln of x, divided by a positive value, and then all of this is multiplied by x over 1 over x, which is positive. So negative divided by positive times positive, which means the entire expression is negative. So dy dx, which equals x to the 1 over x times 1 minus ln of x over x squared, is strictly less than 0 for all x greater than or equal to 3. So since the derivative of x to the 1 over x is strictly negative for x greater than or equal to 3, this means x to the 1 over x is strictly decreasing for x values greater than or equal to 3. So we have established that f of x is strictly decreasing for all x greater than or equal to 3. This means f of 100 is less than f of 99. So this implies 100 to the power of 1 over 100 is less than 99 to the power of 1 over 99. And this is equivalent to saying the 100th root of 100 is less than the 99th root of 99. So the 99th root of 99 is the greater of the two expressions.